So now I want to introduce our speaker of semi-plenary session. So it's my great pleasure to introduce Dr. Kyoung-Whan, an assistant professor at the Yonsei University, South Korea. Dr. Kim completed his PhD at Post-Tech on 2013 under the supervision of Professor Kyoung-Whan. He did his postdoc at NIST and JGU Mines with Dr. Mark Stiles and Hiro Sinova. From 2018 to early 2024, he served as a senior researcher at the Center for Spintronics, AIST, before joining Yonsei University as an assistant professor in March 2024. Dr. Kim's research focusing on theoretical spin and orbital transport, magnetization dynamics, and spintronics application has earned him many accolades, including the Young Researcher Award from the Asian Union of Magnetic Society, the Hyundai Physics Award from the Korean Physical Society, and the Outstanding Research Award from the Korean Magnetic Society. So now, very warm welcome to our session on this international conference. So now yeah, you can.
Yeah. Thank you very much for the kind introduction. It is very honored to be invited here. So what I'm going to talk today is the dynamics of orbital angular momentum in non-equilibrium solids. And as some of you might know, the field of orbitronics is one of the most attractive subfield of spintronics so I would like to introduce the dynamics of orbital angular momentum in non-equilibrium solids. Here, what I mean by non-equilibrium is that due to so-called the orbital quenching, which appears in the textbook level of solid-state physics, in most solids, the orbital angular momentum expectation value is 0 in equilibrium. But in non-equilibrium, a large amount of orbital angular momentum can arise by applying an external electromagnetic field. So I would like to introduce their dynamics, particularly focus on the difference from the dynamics of spin angular momentum. So let me start with my introduction on the spin angular momentum part first. You know, the generation of a spin current is particularly important, not only for fundamental science, but also for spintronic applications. And the traditional ways to generate spin current includes utilization of spin polarization of a ferromagnet or spin pumping induced by the magnetization dynamics and spin motive force, and so on. Here, please note that these methods utilize the exchange interaction of a ferromagnetic material. On the other hand, around a decade ago, another way to generate a spin current, which is called the spin Hall effect, has received a great attention in our community. The phenomenology of the spin Hall effect is that when you apply a charge current through a strongly spin orbit coupled material along this direction, then you may obtain a transverse spin current, which is perpendicularly flowing to the injected charge current direction. And the origin of the spin Hall effect is the spin orbit coupling of this material, which makes the spin up going up, spin down is going down, or the other way around. And the efficiency of the spin Hall effect is quantified by so-called spin Hall angle, which is calculated by the generated spin current divided by the applied charge current. And its magnitude is known to be on the order of a few percent, but it can be even larger than 100%. So it's very large effect. Therefore, it would be very interesting to look at the physical mechanism of the spin Hall effect, particularly for the intrinsic part. Here, what I mean by intrinsic is it is coming from the electronic band structure itself, not the extrinsic contributions like the scattering potential and so on. And a famous model describing the intrinsic spin Hall effect is the Rashba model. And this Rashba model is a physical model describing the electrons near the interface between two different layers where a strong symmetry breaking along this direction is present. In this situation, it is known that spin interact with the so-called chiral spin texture, which is denoted by this K cross Z direction. So spin prefers this kind of direction. This is called the spin texture in the K space. And in the presence of spin texture, when you apply an electric field along X direction, then the Fermi surface is shifted a little bit. Then this shifted spin direction is deviated from its original eigenstate direction, which is depicted by this orange direction. So we can deduce that these black spins, shifted spins will precess around these orange spins, generating spin up here and spin down here. So you can see that since this is a K space, spin up is going up, spin down is going down. This is nothing but the spin Hall effect. And it is also known that the intrinsic spin Hall effect driven by the Rashba interaction is large enough to supply the sufficient spin angular momentum to an adjacent ferromagnet to switch its magnetization direction from up to down direction. But one of the problems of this way of understanding of intrinsic spin Hall effect is that when you carry out the calculation of spin Hall conductivity for centrosymmetric materials, or when you do your experiment with centrosymmetric material, then you obtain a non-negligibly large spin Hall conductivity. But this large Rashba model requires a symmetry breaking. So this kind of understanding requires a symmetry breaking. So it cannot explain what we are measuring in your experiment or what we are calculating in our calculations. But it is known that it is mathematically proven that we cannot find a spin texture model in centrosymmetric normal metal unless we introduce another degree of freedom. So this is the scenario accepted by our community. So these are the representative degrees of freedom of electrons in solid, crystal momentum, spin angular momentum, and orbital angular momentum. Then when we apply an electric field, we have some crystal momentum dynamics. But in centrosymmetric normal metal, it is mathematically proven that there is no direct coupling between spin angular momentum and crystal momentum. So if we want to generate a spin dynamics like spin Hall effect by an external electric field, we need to bypass through another degree of freedom. One of the representative examples of this bypassing degree of freedom is the orbital angular momentum degree of freedom. So it is indeed known that the crystal momentum and orbital angular momentum are coupling through so-called orbital texture, which I will introduce later. And so when you apply an electric field, the orbital dynamics arises first, for instance, orbital Hall effect. And such an orbital dynamics is transferred to the spin angular momentum through spin-orbit coupling of the material. So there are two important points of this slide. The first one is that the orbital angular momentum is a more fundamental dynamics than spin angular momentum dynamics because it occurs first and transferred to the spin angular momentum through a spin-orbit coupling. And indeed, a time-dependent DFT calculation for a particular material under an applied electric field explicitly shows that the orbital dynamics arises first and the spin dynamics arises later. The another point is that the presence of the orbital dynamics is much more general than that of spin angular momentum dynamics because when you want to have large spin Hall effect, we need to have large spin orbit coupling. However, for the orbital part, this one is not essential. And I will tell you the orbital texture is everywhere in solid. So large orbital angular momentum dynamics can be present even in the absence of spin orbit coupling. So the presence of the orbital dynamics is much more general. Then what is the orbital texture? Orbital texture is what I want to call the K-dependent orbital states within a single band. For instance, when you see this radial p-band or tangential p-band, in this p-band, the electron eigenstate is py here, but px here. So for the different K point within a single band, the orbital eigenstate are different. Then due to the time limitation, I have to skip the microscopic origin of the orbital texture, but at least I want to say that in order to derive the existence of the orbital texture, you don't need to assume any kind of specific material property or symmetry breaking. You just can assume the presence of the lattice structure and some hybridization mechanism of the orbital angular momentum states, which are present everywhere in solid. So the orbital texture is everywhere in solid. When you have a lattice structure and several first principle calculations done by our colleagues, explicitly showed the k-dependent orbital property even within a single one. So this is quite general. So let me show you the orbital dynamics arising from the orbital texture. So as I told you, I would like to focus on the qualitative difference between orbital angular momentum and spin angular momentum, because the spin angular momentum and orbital angular momentum are orbital angular momenta. Therefore, the measurement technique for the spin angular momentum and the orbital angular momentum are the same. For instance, magneto-optical Kerr effect or spin torque measurement, all of the techniques are the same. Then, when you want to claim that we are measuring the orbital signal, then we need to quantitatively analyze their signal, which is in general very difficult. So it would be very convenient to have the qualitatively different dynamics of orbital angular momentum from the spin angular momentum. And one of the qualitative difference between spin and orbital is the angular momentum quantum number, which is 1/2 for spin and which is greater or equal to 1 for the orbital angular momentum. So for a spin angular momentum having the angular momentum quantum number 1/2, any spin-related operator can be expanded in terms of these Pauli matrices. And the first term corresponds to the charge part, and the other terms gives you the spin part of the operator. For instance, when you have a velocity operator, you have charge current and spin current. When you have density operator, you have charge density and spin density. But for the orbital case, even for the simplest case of the p orbital, we have a 3x3 matrix. Therefore, it is expanded at least in terms of 9 terms. And for 5x5 matrix for d orbital, we need to expand it in terms of 25 matrices. So 4 of them can be assigned to charge part and orbital angular momentum part. Then what about the 5 more terms? These 5 more terms are represented in terms of the second order product of orbital angular momentum operator, which is absent for spin angular momentum part. Therefore, these guys does not have any spin counterpart to the spin counterpart. Therefore, we can conclude that there are additional degree of freedom not corresponding to charge part and angular momentum part, and these additional degree of freedom will give rise to a kind of orbital dynamics which does not have any spin counterpart, because the second order product are the 0 or 2 for spin angular momentum. So in order to look at the important role of the second order product, we wrote down a general p orbital Hamiltonian for time reversal symmetry and central symmetry. And the first term gives you the orbital independent Hamiltonian, and the second term is the orbital dependent Hamiltonian, and this orbital dependent part is written in terms of the second order product of orbital angular momentum dynamics. Here, this term, therefore, exists only for orbital, so it does not have any spin counterpart. And what is the physical origin of the second term? This physical origin of the second term is nothing but the orbital texture, because, as I told you, orbital texture is a k-dependent orbital property. And this gives you the orbital property of electrons, because this is depending on the orbital angular momentum operator. And this coefficient, H2, gives you its k-dependent. So k-dependent orbital texture, orbital property. This is the orbital texture, and the orbital texture is known to originate from the crystal field splitting, whose energy scale is on the order of electron volts, which is very large. So this is large, but no spin counterpart, so it seems quite important. Therefore, we wrote down the Heisenberg equation of motion for orbital angular momentum driven by this Hamiltonian to look at the dynamic role of this second order product. And we conclude that when we inject an orbital angular momentum to a time reversal symmetric and central symmetric material, this orbital angular momentum is converted to a something described by the second order product, and the physical meaning of this something will be introduced later. And this something, second order product, is getting back to orbital angular momentum. Therefore, as a result, the orbital angular momentum is oscillating in time when you inject inject it into a time represent symmetric and central symmetric material. However, for spin angular momentum, spin does not have any second order product. Therefore, spin does not oscillate in time in this system. So the orbital dynamics and spin dynamics are qualitatively different. And this is the toy model example for this oscillatory behavior of orbital angular momentum and spin. It's different from spin angular momentum, but let me skip this due to the time limitation. So as a result, when you inject an orbital angular momentum to a central symmetric normal metal, the angular momentum is oscillatory. And when you introduce a diffusive mechanism, it is oscillatory decaying, while the spin angular momentum is monotonically decaying. However, for spin angular momentum part, it is known that the spin can be oscillatorily decaying when you're applying a magnetic field or introduce exchange interaction or Rashba interaction and so on. But please note that these guys break some symmetry, time reversal symmetry, central symmetry. But for this oscillation, the orbital angular momentum oscillation does not require any kind of symmetry breaking. So this oscillation does not have any spin counterpart, which is qualitatively different from the spin dynamics, and the relevant energy scale is large and its presence is quite general because it does not require any symmetry breaking. And let me introduce another degree of freedom of orbital angular momentum to describe this oscillatory dynamics by introducing so-called orbital angular position. And in order to understand what the orbital angular position is, it is convenient to understand the orbital quenching first. So from when you consider a single hydrogen atom in the textbook level of quantum mechanics, it is known that when you solve the Schrödinger equation, the eigenstate is given by orbital angular momentum state, which is described by the spherical harmonics. However, in the textbook level of solid state physics, since you have a lattice structure, their eigenstate does not have any orbital angular momentum expectation value in most cases. This is called the orbital quench. Then what are the differences between them? To understand this, let us forget about any angular degree of freedom and consider something that we are familiar with. For instance, when you consider a continuously translational symmetry with constant potential, then when you solve the Schrödinger equation, this momentum state, plane wave state is the eigenstate. This is quite well known. But when you put some strong potential source to break the translational symmetry, then it is known that their position localized state, what I would like to call position state, or their linear combination, bonding state or anti-bonding state, are the eigenstate of this state. And in the presence of some discrete symmetry, like parity symmetry, it is known that these guys does not have any momentum expectation value. Momentum expectation value is 0. The same thing happened for the angular part. So when we consider the single hydrogen atom, then the continuous rotational symmetry gives you the angular momentum states as your eigenstate as described here. But when you have a lattice structure, due to this lattice potential breaking the rotational symmetry, your eigenstate is now a angular position state where the electronic wave function is localized at a particular angle. So although these guys have 0 angular momentum, all of these guys have 0 angular momentum expectation value, their angular position are different. So this is localized here, here, but this guy is localized here, 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 here. This one represents this potential, plus minus. And in the presence of a kind of discrete symmetry, which is frequently present in most solid states, the angular momentum expectation value is 0 for this orbital angular position state. So in this sense, the orbital angular position is much more provides a fundamental property of electron eigenstate in solid. So by using this definition of orbital angular position, we can realize that this tangential p orbital texture is nothing but the orbital angular position texture, because for py band here, the wave function is localized along the y direction. For px band, it is localized along the x direction. So this is the orbital position texture, and this is the Rashba type orbital angular momentum texture. And as I told you, presence of orbital texture does not require any symmetry breaking, and energy scale is quite large. But for the orbital the angular momentum texture, it requires symmetry breaking, and the magnitude is small. But most importantly, the angular momentum texture presents both for spin and orbital. Spin angular momentum texture and orbital angular momentum texture. However, for angular position texture, it exists only for orbital because spin does not have any angular position, because spin is an independent degree of freedom from the special part of the wave function. And let me skip this part, but summarizing the conclusion, the second order product that I tell you, which is important, is nothing but the orbital position degree of freedom. So when you take the expectation value of the second order product of orbital angular momentum operator, it gives you the orbital angular position. This provides another reason why spin does not have any angular position, because the second order product of Pauli matrix gives you a trivial result. Now, by introducing this orbital angular position degree of freedom, the oscillatory behavior between first order and second order product becomes now natural. For instance, when you inject an orbital angular momentum to a central symmetric solid, this orbital angular momentum state will be tilted from its equilibrium direction, and this kind of torted direction, torted electronic state tends to get back to its original eigenstate. And during this harmony oscillation, this oscillatory behavior between orbital angular momentum and orbital angular position becomes quite natural. And this one is the first order product of orbital angular momentum, and this one is the second order product of orbital angular momentum. This one is quite similar to the classical torsion pendulum here. So let me give you some introduction of the orbital transport phenomena originating from the orbital angular position degree of freedom. So the first example is the orbital Hall effect. So when we have a orbital texture, this tangential p-band is just a particular example, but this argument holds for all type of orbital texture. So when you have an orbital texture, suppose that you apply an electric field along x direction, then the Fermi surface is shifted a little bit. Then this shifted electronic state is now a little bit tilted from this original eigenstate given by this tangential direction, right? So this orbital angular position is a little bit torted to anti-clockwise direction for ky, a positive ky direction, but for here, this angular momentum is a little bit tilted toward the clockwise direction. So this torted electronic state tends to get back to its original state, right? You want to rotate to this direction. During this process, you have this angular momentum down here and angular momentum up here. So you have angular momentum down for positive ky, you have angular momentum up for negative ky. It gives you a kind of the orbital Hall effect. And in the presence of spin orbit coupling, this orbital Hall effect will be transferred to the spin Hall effect. And this kind of explanation gives you a nice explanation without any single mathematical equation on the spin Hall effect arising from the central symmetry normal metal. So it is known that the main mechanism of this, the intrinsic spin Hall effect in the central symmetric normal metal is originating from the orbital angular momentum degree of freedom. And the orbital angular momentum Hall effect can be measured by the magneto-optical curl effect or spin torque measurement. But anyway, they are measured. And let me skip this orbital torsion Hall effect due to the time limitation. Also, you can inject an orbital angular position current or the torted orbital state by using a kind of twisted structure. For instance, when you prepare the twisted structure, something like this, then electronic eigenstate here and electronic eigenstate there are a little bit tilted with each other. Therefore, when you apply the perpendicular voltage, you can inject an orbital torsion, non-equilibrium orbital angular position, a little bit rotated non-equilibrium orbital state, then this is converted to orbital angular momentum because their mutual oscillatory behavior. In this way, you can generate an orbital angular momentum accumulation here, which can be detected by the optical measurement or electrical measurement. And an interesting feature of this the measurement scheme is that we don't have any ferromagnetic material or spin related the degree of freedom, but we have an angular momentum signal which is measurable here. So this is originating from the orbital angular position degree of freedom. And another example where the orbital angular position degree of freedom is important is the spin relaxation part. So for spin relaxation, it is known that there are two main mechanisms called Elliott-Yaphe mechanism and Jackonov-Perel mechanism. And for this Jackonov-Perel mechanism, it is known that when you break a symmetry, I mean invergent symmetry breaking, you have a spin texture, and in the presence of this spin texture, and when you inject a spin angular momentum, this spin angular momentum tends to precess around this spin orbit field. This is called a spin orbit precession, and it gives you the origin of a spin relaxation mechanism. So this is called the Jackonov-Perel mechanism. So when you inject a spin angular momentum to an invergent symmetry broken material, then due to the spin orbit precession, you have a spin relaxation mechanism whose rate is proportional to the momentum scattering time. So it is believed that the Jackonov-Perel mechanism originates from the invergent symmetry breaking. However, when you accept the concept of orbital angular momentum and its oscillatory behavior with the orbital angular position degree of freedom, this orbital angular momentum can oscillate in time even without requiring any symmetry breaking. So when you inject an orbital angular momentum to a central symmetry normal metal, then orbital angular momentum is oscillating in time in the same way as the spin oscillation here. Therefore, this orbital oscillation gives you another type of orbital relaxation mechanism. Something can be called the Jackonov-Perel-like, and this orbital relaxation rate is proportional to the momentum scattering time. So this gives you the generalized picture of the Jackonov-Perel-like relaxation, spin relaxation, and orbital relaxation, even in the absence of the symmetry break. And another example where the orbital angular position can be important is the orbital pumping. So as you might be familiar with, for the spin pumping, you have a kind of magnetization dynamics, for instance, angular momentum dynamics. Then you pump a spin angular momentum to an adjacent material. So this is some angular momentum to angular momentum pumping. But for orbital angular momentum, we have angular momentum and angular position. Therefore, angular momentum dynamics can pump angular momentum and angular position, and angular position dynamics can pump angular momentum and angular position. So 3 more paths are possible, and these guys do not have any spin counterpart. And the angular position dynamics can be generated by some lattice dynamics because angular position is originating from the lattice structure. So when you inject a kind of phonon, something like that, then you can generate some angular position dynamics. And this angular position dynamics give you a kind of interesting source of pumped orbital angular momentum or pumped spin angular momentum when you introduce spin orbit coupling. Though these guys do not have any spin counterpart, as I told you. And one of the interesting feature of the orbital pumping is that when you generate the dynamics of orbital angular momentum with frequency omega, this inverse orbital Hall effect frequency the signal can give you the 2 omega signal, which is impossible for spin angular momentum pumping unless you have the spin orbit coupling parameter, which is very comparable to the exchange coupling parameter, which is yeah. So for the spin pumping, conventional spin pumping, it gives you a DC signal or omega signal, but for the angular momentum, orbital angular momentum pumping, it gives you a kind of 2 omega signal. So when you measure something like this, this is a qualitative difference from the spin angular momentum dynamics. So we can say that this is an orbital signal without making a very detailed quantitative analysis. So to summarize my talk, the orbital angular momentum, since orbital angular momentum and the spin angular momentum are both angular momenta, they seem quite similar, but there is some important difference. The presence of the another degree of freedom called orbital angular position, and its origin is crystal field splitting, physical, and mathematically it is coming from the non-trivial anticommutator of the orbital angular momentum operator. And this novel degree of freedom is not only helpful for understanding the orbital transport, but also helpful for distinguishing the orbital dynamics from spin dynamics. So yeah, you can easily claim this is an orbital signal without making a quantitative analysis. So this is the end of my presentation, and thank you for your kind attention.
Thank you, Dr. Kim, for the fascinating presentation. We'll now open the floor for questions. We have time for 2 more questions before we wrap.
Oh, well, Prof. King, it's very nice talk. I have a question. So in slide 10, you talked about some extra term in the orbital Hall current. And then in the slide 12, in the figure you show of the oscillation of the orbital current in slide 12.
Okay.
Yeah, so here the x-axis is it's the time scale, right? So what's the time scale of the oscillation?
Time scale of the oscillation depends on the energy gap between two different orbital states. So it is in general very fast. It is kind of, if you have very large energy difference, it is kind of femto, which is very difficult to measure. And if you have a kind of, if you have a small gap semiconductor, something like that, you can make this something measurable. But still, I have to say that this frequency scale is very high.
Okay, so is it like possible to detect with terahertz to check the spectrum?
Yeah, if you have the low gap semiconductor material, it can be measurable from terahertz. At least the time scale is on the order of that. But if you have a large gap, terahertz signal is still insufficient.
Okay, thank you.
Questions? Okay, so I have a question. So most of the case before orbital angular momentum was largely known. So how do you see that this newfound understanding will impact the design or optimization of running device in the future?
The sound was a little bit howling. So are you asking the optimization roadmap of the spintronic device by using the orbital angular momentum degree of freedom, something like that?
Yes.
Yeah.
Yes.
I think there are two ways. The first way is the quantitative thing. So in general, when you use the spin Hall effect as a spin generator, it is a general tendency, there is a general tendency that the largest spin Hall material have the large resistivity. So when you want to generate a large amount of spin current, the resistivity goes up, so energy efficiency becomes going down. There is a dilemma between resistivity and spin Hall conductivity. But for the orbital degree of freedom, such a constraint is relaxed, because the reason why the high spin Hall material has a high electrical resistivity is that the spin-orbit coupling is large. However, for the orbital part, it does not require any spin-orbit coupling. Therefore, for the low resistivity material can have large orbital Hall signal. In this sense, we can realize the spin-orbit material and spin-orbit devices with much higher energy efficiency. That would be the first way. And another way is that which is quite primitive, but this kind of physics does not have any spin counterpart. So if there are some guys who are smart enough, then they can devise another type of the architecture for spin orbit devices with a new paradigm, which actually, frankly speaking, I have not come up with until now. But such a way would be another promising way to use the orbital angular momentum degree of freedom. Oh, your mic is off.
Yeah, so sorry. So thank you so much for an interesting talk and interesting methods from your talk. And yeah, so and if we still have time, if you have any questions from the participants, we can take more question. One more. No. Okay. Yep. So.
Oh yeah.
Yeah.
Thank you very
Okay.
much. Yeah.
Yeah. Thank you. Thank you for your time.